In 4.6, we're going to be looking at exponential and logarithmic models, or applications of what we're working with in our logs and exponentials. And so we're going to be looking at exponential growth and decay equations. Now, we've already experienced some with this AB to the T, but if we're talking about it continuously decaying, what some of your problems will state, then we're going to be using this AE to the RT. Also, many times in scientific tests, they're going to use this E as they go to determine decay within their scientific test of figuring out the life or growth or decay of certain items. And so let's experience and work with some of these problems of AE to the RT. So it says a certain bacteria population is known to double every 90 minutes. Suppose that there are initially 80 bacteria. So that's important there. Initially 80 bacteria. That's going to be our A, as you've seen in other problems. Write an expression that models the size of the population after T hours. So in order to work this problem, the first thing we're going to do is we're going to find R. And so in order to find R, let's think about what's happening here. So this is going to be equal to 80 E to the R. Now our time, it says is 90 minutes. So 90 minutes would be 1.5 hours because it says after T hours. So I'm going to use 1.5 here. Then it says that it's doubling during that time. So I would say twice 80 would be my double. Using all the information that's given, you can see now the only variable I have is R. Remember, E is a number. And so I'm just going to go ahead and solve that out. So if I divide both sides by 80, those would cancel, and I get 2 equal to E to the 1.5 R. In order to pull that variable out of the exponent, I'm going to have to ln both sides, as we saw in previous sections. So I get ln 2 equal to 1.5 times R, and then divide by 1.5. And so this would be my R value. Now that I have my R value, I'm going to leave it as an exact fraction. I don't want to go over here and plug it into a calculator because I'm going to have to use it to evaluate some other items. So I want to make sure I'm using exact values, not around it from my R, and then I have a ton of rounding as I move forward. And so for step 2, what I want to do is step 2, I want to plug R into the equation. So I have f of t equal to 80, my initial value, E from my formula, R, which is ln 2 over 1.5 to the t. And so I have now found the equation or expression that models the size of the population after T hours. Let's look at another one, a little bit different formatting of the information. It says the half-life of radium-226 is 1590 years. If a sample contains 200 milligrams, how many milligrams will remain after 1,000 years? And so we're going to follow the same steps as we did in the previous example. The first step we want to do is we want to find R. In finding R, let's look at what's happening. So it says the half-life is 1590. The sample contains 200 milligrams. How many will be left after 1,000 years? So half of 200 would be equal to 200, my initial value, E to the R, and that's after 1590 years. And so I'm just using this piece of information here. So if I divide both sides by 200, I get 1/2 is equal to E to the 1590 R. I'm going to ln both sides. So it gives me ln of 1/2 is equal to ln E cancels out, so 1590 R, and divide by 1590. So very similar to what we were doing in the previous one, but it was a half-life instead of a doubling. So number 2, you're going to plug your values into the equation. When I plug those values into the equation, I get f of t is equal to 200 E. Now my R is ln of 1/2 over 1590 t. So that's my expression. But this says how much will remain after 1,000 years. So now we're going to take 1,000 and plug it in for here for t. So be very careful with your calculator. You've done really hard to create this equation. Don't let a calculator error cause you to miss this problem. So this is going to be times 1,000. So what I would do is in my calculator, I would type in this number here and get that value. Times 1,000. Raise e to that answer and multiply that times 200. And you should get 129.331 milligrams. So I would encourage you to work through these processes with your calculator, type it all in, make sure you're getting that 129 that we're looking for, so that if you don't get 129, you can correct your steps. Then we go to another problem and you're plugging it in. You know that your steps and your punching is correct, and you feel certain about that answer because you could replicate my steps to get 129. Now I think, again, let's just keep experiencing some problems and see what we're going to see. The next one is a wooden artifact from an ancient tomb. It contains 35% of the carbon-14 that's present in living trees. How long ago to the nearest year was the artifact made? And so it says the half-life of carbon-14 is 5,730 years. So again, same steps. First one, I want to find my R. So in order to find R, we've already seen that half-life would be equal to e to the rate times time, and we know half-life is 5,730. So we're going to solve it like we did in the previous one. So ln. So it gives me ln of 1/2 is equal to, that's inverse function, 5,730 R, and divide. So R is equal to ln of 1/2 over 5,730. So step 2, let's plug it all in. And so this gives me the equation of looking at this one, it's going to be a little bit different for us because in the previous one we had initial value. With this one, it just says a wooden artifact contains 35% less, and so it doesn't tell you the original or initial amount. So let's think about what's happening here. If we had an initial amount of 100%, that would be 1. So that 1 times our E times our rate of ln of 1/2 over 5,730 times t would be equal to 35% or 0.35. And so if I consider those percents to be decimals, I can create this without having to know that initial value. Now I can solve it from here. So I could say ln of both sides. So ln e would cancel. And I get ln of 0.35 is equal to ln of 1/2 over 5,730 t. And then I could divide by that ln of 1/2 over 5,730. Real big number there. Those would cancel. Over here, when I divide by a fraction, it's like multiplying by its reciprocal. So I'm going to flip it and multiply those two together. So t would be equal to, now go slow when you're using a calculator, type this number in, times type this number in, and this gives you 8,678.5. So it says 8,679 years ago is when, how old that wooden artifact was, without having to know its initial, or we know that it contained 100% of the carbon-14 when it started, and as it decayed down, we were getting down to 35%. So that one's a little bit unique because it's not necessarily just a given milligrams or value we're starting with, but just looking at the carbon dating of it. Let's look at a next example here. We got 3 more to go. It says find the time required for an investment of $5,000 to grow to $7,400 at an interest rate of 7.5% per year, compounded quarterly. So let's go back to what we know. When we're looking at compound interest, let's pull that formula. A of t is equal to p parentheses 1 plus r over n to the nt. Let's think about what we know from all this. We know that we are starting with an investment of $5,000, so that's going to be our principal. And we know that we're growing to 7,400, so that's what we want it to be equal to. We know that we are at an interest rate of 7.5%, so 0.075 when we go to decimal. It's compounded quarterly, so our n is going to be 4, and then 4t. And it says find the time. So now we can solve for this variable up here. Now go slow when you're solving for this. So I'm going to divide both sides by 5,000. So that gives me 7,400 over 5,000 would be 74 over 50 equal to 1 plus, let's go ahead and find that number. So in your calculator, we're going to do 0.075 divided by 4, add it to 1, and you get 0.01875 to the 4t. Now, whenever you have a variable up in the exponent, you want to use your exponential logarithmic problems to get you there. And ln on both sides, you can see is kind of my fave. So I'm going to do ln on both sides. So it gives me ln of 74 over 50 equal to ln of 1.01875 to the 4t. Now the reason I want to natural log this one is because now that I have a log, by my exponent property, I can bring this exponent out front. And so then I have ln of 74 over 50 equal to 4t of ln of 1.01875. And now I can solve for that t. So I'm going to divide by that ln. Now you have to use your calculator with this. And then I'm going to have to also divide by 4 to cancel that 4. Slowly use your scientific calculator to get this. And this gives you 5.28 for your time. So after 5.28 years, we would have accumulated that $7,400 that we were trying to get to. So again, we're pulling up stuff we're doing and we're using it with those log properties in order for us to solve for new variables in different places. 2 more. Bismuth 210 is an isotope that decays at about 13% each day. What is the half-life of a bismuth 210? So let's see what we got. We're going to start with half-life like we've been doing. So I'm going to say 1/2 is equal to E. Let's see, the rate is going to be 0.13. We're decaying, so we're going to be negative T. So now we can solve for time of how long it takes to get to half of my initial amount. So in order to solve this, I'm going to have to ln both sides. So I get ln of 1/2 is equal to ln E would cancel, negative 0.13t, and divide. Hopefully, you're seeing patterns and processes of what we're doing. Calculate that, 5.332. Now it said that this is each day, so it would take about 5.332 days, approximately, to get to the half-life of bismuth. 1 more. Cancer cells sometimes increase exponentially. If a cancerous growth contained 300 cells last month and 360 cells this month, how long will it take for the number of cancer cells to double? So let's slowly work through this one. So first thing that we're going to do is we are going to use f of t equal to ab to the t. Now the reason I want to use this one is if you remember when we go back, when we have 2 sets of data, we can go back to our exponential equation and solve for our a's and b's. And that's what we're going to do here. So our first set of data says that it contained 300 cells last month and 360 cells this month. So let's create our 2 ordered pairs. So that would be 0 month would be 300 cells, and after 1 month it would be 360 cells. And so let's find B. And so I'm going to take those two. I'm going to say f of t is equal to, I initially started with 300, b to the t. And then I know, using this data here, that starting with initial of 300, b, after t to be 1, I'm left with 360. So divide. So b would be equal to 360 over 300 because b to the first power is just b, and that reduces to 6 over 5. Now step 2, we want to find the doubling time. Our equation is we've got f of t is equal to 300 times 6 over 5t. So to find how long it takes us to double, well, doubling of 300 would be 600. And so let's solve that out. So divide by 300. So it gives me 2 equal to 6 over 5t. And then to get that variable out of the exponent, I'm going to have to ln both sides. So that gives me ln 2 equal to ln of 6 over 5t. Now we can apply that exponent property. I can bring that t out front here. So I get ln 2 equal to t times ln of 6 over 5 and divide. So then t would be equal to, we're going to plug that in our calculator, and you get about 3.802 months. So this section did not have a ton of properties or anything like that, but it definitely just kind of pulled everything that we have been working on in this chapter together. So again, go and try all the homeworks. Let me know if you have any questions as you're working through that.